Hello, in today's video we're going to finish our discussion on partial fraction decomposition. So in our first two videos for section 10.7 we discussed the initial process of factoring your denominator and then setting up your decomposition with numerators a and b over the factors of your denominator. I'm going to ask you to go ahead and pause the video and recall that process now by completing numbers 1 and 2 here on your own. So my first step is to factor the denominator. So I've got 4x plus 2. In my denominator, when I factor, I've got x times x minus 2. So I'm going to decompose this into a over our first factor x, and that does have a degree of 1, which means my numerator would have a degree of 0, plus and b over x minus 2. Again, the degree of that factor is 1. So I have a degree of 0 in my numerator. Now to solve for a and b, I'm going to multiply the left and the right hand side by the LCD, which is x times x minus 2. On the left hand side, that fraction is going to reduce completely, and I'm left with just 4x plus 2. On the right hand side, I'm going to go ahead and distribute. When I distribute to my a term, the x reduces, and I'm left with a times x minus 2. And when I distribute to b, my x minus 2 reduces, and I'm left with plus b times x. Now I will simplify that right-hand side by distributing ax minus 2a plus bx. Now, so that I can match my coefficients, I'm going to go ahead and group my x terms and factor out the x. So I've got x times a plus b, and then my constant is a minus 2a. So on the left-hand side, I see that the coefficient on x is 4, which means that we must, on the right-hand side, be multiplying x by 4, so a plus b must be 4. And the constant term on the left is a positive 2, which means on the right-hand side, my constant term, or the component with no x, must be equal to positive 2. So I can write two equations. The first is that a plus b must equal 4. And the second is that negative 2a must equal 2. And this is fairly straightforward. I can go ahead and solve for a, and I get negative 1. And I go back and plug that in for a in the other equation. So negative 1 plus b is 4, which means that b is going to be 5. So then my partial fraction decomposition, I've got 4x plus 2 over x squared minus 2x is going to be equal to a, which is negative 1, so negative 1 over x, plus, and then b, which is 5 over x minus 2. So if I were to add these two fractions back together, I would get that original expression that I started with. For number 2, I factor the denominator and see that I get 5x plus 4 squared. And then I write out all of my terms. So my first is going to be a over 5x plus 4. And since we have that to the second power, I must also have b over 5x plus 4 squared. That factor itself only has a degree of 1, which means that in the numerator of both my fractions, I'm going to have a degree of 0, so just constants. Now here I multiply the left and the right-hand side by the LCD, which is 5x plus 4 squared. And on the right, I do the same. On the left, that denominator reduces completely. On the right, one of those 5x plus 4's reduces with my a term, leaving me with a times 5x plus 4. And both of them reduce for my b fraction, so I have just b with that entire factor reducing. On the left-hand side, I've got 25x plus 18. I now am going to distribute so that I can combine my x's and my constants to match coefficients. So 25x plus 18 is 5x times a plus 4 times a plus b. So it looks like my coefficient on x is 5 and a on the right-hand side, and on the left, that coefficient is 25, which tells me that 5a must be equal to 25. My constant term on the left is 18, and on the right, my constants are 4a plus b. So 4a plus b must equal 18. Solving that first equation, I can find that a must equal 5, and then substituting in that 5 into my second equation, 4 times 5 plus b is equal to 18, which means that b is negative 2. So then my partial fraction decomposition would be a, which is 5 over 5x plus 4, plus b, or minus, since our b is negative, 2 over 5x plus 4 squared. What we're going to do now is a very similar process. We are going to still be working with partial fraction decomposition, but we are going to talk about a couple of new cases. The first new case is when we factor the denominator. So I've got x squared plus 5 minus 7x. When I factor that denominator, one of my factors is a quadratic. Since this factor is a quadratic, that's going to change our setup for our fractions on that right-hand side. So on the right, I would have a over x, and on the right, my denominator would be x squared plus 5. But we have talked about how our numerator needs to have a degree of 1 less than the denominator. So that means this degree needs to be 1. So what I'm going to do is remember that my degree of the numerator must be 1 less than the degree of the denominator. So I'm going to go ahead and write this as b times x. So now it has a degree of 1, but there may also be a constant term. So I'm going to write my numerator as b times x plus c, which is just standard form of a first degree polynomial. So now on the left and the right hand side, I can multiply by that LCD. On the left, my fractions reduce completely, and I've got x squared plus 5 minus 7x is equal to, on the right, my x is reduced completely with the a term, giving me a times x squared plus 5. And with the b term, the x squared plus 5 reduces, leaving me with positive bx plus c multiplied by x. And now I distribute and match my coefficients. So x squared plus 5 minus 7x is equal to ax squared plus 5a, plus, distributing my x, I get bx squared plus c times x. I'm going to combine my x squareds and factor out that x squared to get a plus b. And then I have only one term with a x, and then my constant term is just 5a. So now I can match coefficients on the left. I'm going to write this in standard form with my negative 7x coming next, plus 5. So x squared has a coefficient of 1, which means that a plus b must equal 1 since we are matching those coefficients. My x term has a coefficient of negative 7, which means that c is going to be a negative 7. And then lastly, I have a constant term of 5 on the left, which means that on the right, my constant term must also be 5. So 5 times a is going to equal 5. And I can solve. So I already have c. I now need to find a and b. So I can find a by dividing by 5 in this third equation, and a is going to equal 1. Now I can go back and substitute that in for a to get 1 plus b is equal to 1, or b is equal to 0. Which means that when I replace these values into my partial fraction decomposition, I replace my a with a 1, so 1 over x, plus 0 times x, plus c, which is a negative 7, so I'm going to write minus 7, over x squared plus 5. Now the only thing I can do from here is to simplify by saying that that 0x is actually just 0, which leaves me with a negative 7. So then this would be my partial fraction decomposition of our original expression. Go ahead and take a moment to pause the video and try that out on your own here. So factoring, I've got x times x squared plus 4, and in the numerator I've got 2x squared minus x plus 4. So I'm going to set up my partial fraction decomposition. Since the denominator in that second term is an x squared plus 4, my numerator needs to be a first degree polynomial. So in standard form, that would be bx plus c. I multiply the left and the right hand sides by x times x squared plus 4. And then I reduce. So on the left I have 2x squared minus x plus 4 is equal to, my x reduces, leaving me with a times x squared plus 4 plus b x plus c, which I am multiplying by x once my x squared plus 4 is reduced. So I simplify that right-hand side and combine like terms. So I've got ax squared plus 4 times a plus bx squared plus c times x. So 2x squared minus x plus 4. On the left-hand side, I can factor out an x squared from a plus b. And then I have a positive cx and a plus 4a. So the coefficient on x squared is 2. So a plus b would then equal 2. The coefficient on x is a negative 1. So that tells me that c is going to equal a negative 1. And the coefficient for my constant is 4, which means that 4a is equal to 4. So I go ahead and solve for each of my variables. I have c, a then is 1, and plugging that back in, I find that b is also 1. So plugging that back in for a, b, and c, I've got 1 over x. C is a negative 1 and b is a positive 1. So I've got plus 1x minus 1 over x squared plus 4. And this would be your partial fraction decomposition for our original expression. I've got one more for you to try. You can go ahead and practice this one on your own, but I am not going to spend the time going over it because there's one more topic that I want to cover. And that is this. If your degree of your numerator is greater than or equal to the degree of the denominator, we cannot go straight into partial fraction decomposition. In order to use partial fraction decomposition, in order to use this process, the degree of our denominator must be greater than that of the numerator. So I need to go ahead and use long division to simplify. So to perform long division, I go ahead and put that numerator underneath my long division bar, so 2x to the 4th plus 4x to the 3rd minus 2x squared plus x plus 7, and then the denominator goes outside, so x to the 3rd plus 2x squared minus x minus 2. We just focus on that first term and see what do I need to multiply x to the 3rd by to get to 2x to the 4th, and that would be 2x to the 1st power. And then I multiply down. So I've got 2x to the 4th plus 4x to the 3rd minus 2x squared minus 4x. And we subtract. I have just a negative 3x plus 7, it looks like. And that would be a remainder since now this degree is less than that of what I am dividing by. So this division then simplified to 2x. But I have a remainder of negative 3x plus 7. So I put that over my original denominator and add. So now when I perform my partial fraction decomposition, the only piece I'm worried about is this much more simple fraction that we have just created. So I perform partial fraction decomposition there, and then whatever we get, we are just including that 2x onto the front. So if your degree of your numerator is greater than or equal to the degree of the denominator, you just have one step before you go into partial fraction decomposition, and that is to divide so that your numerator has a degree that is less than the denominator, and you can perform your partial fraction decomposition. We're going to go ahead and end our video here. Thanks for watching and have a great rest of your day.